All right, welcome to Full Momentum and HEC RAS podcast. I am your host, Ben Carey. Joining me today, we have Chris Goodell, as always. And we also have a couple really awesome guests on the show to talk about a special topic that we all really enjoy getting into and working on, and that is the projects that are called nature-like fishways or roughened channels. So to discuss that particular topic today, we have our own Tyler Kreider, who's a senior engineer out in Pennsylvania.
Hello.
And then we have Mike Love, who's a managing principal of Michael Love and Associates in California. So welcome, Mike and Tyler, to the podcast.
Welcome, guys.
Thank you for having us.
Yeah, glad to be here.
Good to have you on.
Yeah, so this is a really exciting topic and is one that Chris and I can contribute on the modeling side of things, but we wanted to bring in two experts because this kind of gets out of our area of expertise as we kind of get into the nitty gritty of nature-like fishways. And there's also been a lot of really cool developments and research that's been done on this particular topic, and so we're going to cover some of that today. Before we get into that, though, I do want to provide an opportunity for you two to introduce yourself to the audience here. Talk a little bit about yourself. So Tyler, if you want to start, that'd be great.
Sure. Thanks, Ben. Tyler Kreider. Grew up in Pennsylvania. Never thought I'd continue to work in the state, but here I am. I played in streams as a kid, and I'm still trying to do that for my work and try to get paid on the best days. And so I got an engineering degree, environmental resource engineering specifically, from SUNY ESF in upstate New York, Syracuse, New York. That sort of launched me into this interesting field of environmental resource engineering. Then finished up with a master's degree at Virginia Tech in biological systems engineering. Focused a little bit more on sediment transport and some stream processes work there. And then jumped into a career at Kleinschmidt and have worked on a variety of projects spanning dam removals, habitat restoration, and more recent years, nature-like fishways. So yeah, I'm located near the Susquehanna River in Pennsylvania, and that's where a lot of my work has occurred, and across the Mid-Atlantic. And that's sort of where I come to it. I'm not a heavy HEC-RAS user. I know some of the basics and use a lot of that in undergrad and a little bit through my career. I often turn to Ben and his team and others for some of the detailed work and work with them on the outputs overall. So
awesome
for having us on today.
Tyler, is that the Susquehanna behind you?
That is. Yep.
Yeah.
The most recent fishway I've completed there on the Susquehanna. It's about a half-mile wide at that point, just to give people a sense of scale for those that haven't stood on one bank and looked across it.
Yeah.
Very cool. Awesome. Welcome, Tyler. And Mike, I'll throw it to you next.
Okay. Mike Love. I went to school at Humboldt State University. Similarly, I went through the engineering department there, environmental resource engineering, and now it's called Cal Poly Humboldt. They just renamed it into a polytechnic, and that's up in the northwest corner of California, up in the redwoods. Very different than what most people think of California, and right on the coast. Kind of grew up playing in streams and especially at the beach, kind of manipulating streams as they flowed into the ocean. So really was excited when I learned about opportunities to work actually moving real streams around and doing restoration. So after college, I did AmeriCorps with the U.S. Forest Service.
Oh, very cool.
And that they threw me right out the first month I was there in October, which wasn't a great time of year, up into the Pacific Northwest. The 96 floods had just happened, which was like 100 to a 500-year flood event, depending where you were. And I was sent out with my field partner to do culvert autopsies, we called them, where we would figure out how a culvert failed. We'd dig out the inlet and find the stick that caused it to fail and compare the culvert size to the stream size to the stick that caused the entire road or highway to blow out. Very fun, learned a lot. And then as part of that, after that started working with the Forest Service and AmeriCorps, actually writing the fish crossing software with Mike Furness led the project, and Susan Fire. We wrote the fish crossing software, which is a 1D hydraulic model for culvert hydraulics that routed fish through it. And so that was kind of how I jumped into fish passage, and then was working with Dr. Margaret Lang. We did some research with students and NOAA Fisheries, trying to look at fish passage back in the late 90s and helped develop those guidelines as salmon were being listed as endangered. We needed road stream crossing guidelines. And so everything came from there, and just started a small company, Michael Levin Associates, MLA, and we've got a small crew, very interdisciplinary. I did the 1D RAS thing, but I've kind of passed it on to most of my staff that do the 2D RAS. We do everything. We do the surveying, the modeling, the plans, the specs, the construction management. So kind of get to dive into all that for fish passage and restoration projects in general on the streams and estuaries. So
very cool. Very cool. Well, thanks for that intro, Mike, and welcome to the podcast.
I think that's the first time I've ever heard the two words culvert and autopsy together, which is really cool. Makes me think maybe you've got a television show coming up, like another CSI, could be like culvert scene investigation, maybe. I don't know.
I don't know what the audience would be for that.
It might just be the four of us tuning in, though, probably.
No, it'd probably be everybody that happens to listen to this podcast.
At least for the pilot episode, maybe. I don't know.
Very cool. And my understanding is that, Tyler, you and Mike know each other, right? You guys have met at some conferences or some technical workshops or whatnot. How did you guys meet?
Yeah, so the American Fisheries Society Biological Engineering section had a grant to expand the science of nature like fishways. And so Mike and I and several others collaborated on a Nature Like Fishway workshop hosted by the Salmonid Restoration Federation in California in late March. And so that's where we first met each other. We may have seen each other in passing at a prior conference, but so we really got a chance to collaborate, and then we did it again as a one-day workshop at Fish Passage 2024. I guess that was just last week. So, yeah.
Very, very cool. Well, I'm glad you guys met, and I'm even more glad that you were willing to come on and share some airtime with us today talking about this topic. Before we get into the primary topic for today, I do want to go into a couple listener questions that we received since our last episode release. And before I do that, I also want to recognize and thank everybody who tunes into the show. We just crossed the 150,000 viewer mark on our vodcasts. So this is episode 30. We've gotten on average about 5,000 views per episode. And so anytime we cross a milestone, like 150,000 views, we want to recognize that, because it's pretty cool. We started this 4 years ago and have had that much reach, both nationally and internationally. So it's
and when you get to 150K too, it's not just you and me, Ben, watching. Mm-hmm. There's got to be more people than just the two of us. So
that's right. Yeah, I have my parents watching the channel on loop. That can only count for so many views. So
yeah, that's right.
All right. So first question that we had that we wanted to get into today. This one's an easy one. Chris, I'll let you share your screen because I think that's the best way to answer this. Yeah. And this was based on some of the comments and conversations that we had around the shallow water equations that you need to choose between using the full shallow water equations or the simplified diffusion wave approximation. And somebody had asked, how do you know if you're using the full momentum or the diffusion wave set of equations? How can you verify what your model's using?
Yeah, well, the easiest way to know is just check under options and go to computation options and tolerances. You'll get to your options and tolerances window. Go to the 2D tab right here. And on row number 6, it tells you what equation set you're using for every single 2D area you have in your model. So a lot of people get confused about this. What is this default column? The default column is just what RAS will adopt for any new 2D area you put into your model. But for what's being used for a specific 2D area is under the column header of that particular 2D area. So in this case, we only have one 2D area. It's called reservoir, and you can see that we're using diffusion wave. And so if you want to change it, you would just click here and select the other equation set from the dropdown, whether it's SWE. I don't know why it's not letting me pick that over there. Let me reopen it.
Could it be because of the size of your window, maybe? I don't know if that's
yeah, maybe I messed that up. Okay, there we go. Okay. So you've got diffusion wave, you got the SWE. The listener calls it full momentum, which was the original name for SWE ELM. But then they started having these kind of offshoot or like variations of it. So they changed it to SWE, which stands for shallow water equation. And then ELM, EM, and LIA are three variants of the shallow water equation that we could talk another hour about. But normally, I would say 95% of the time, Ben, wouldn't you agree? We use the ELM for most of our, yeah. So double check on that in this options and tolerances. Not sure that maybe the question was, well, what about looking at output? How would I know? And one quick way to know is look in your output in RAS Mapper. Look for areas where you have significant contraction and expansion of flow. So here we can see we've got this model example. This is actually our workshop from our class. So if you want to learn about this in a little more detail, sign up for our class. But here you can see we've got these obstructions in the middle of, in this case, it's a reservoir, but it could be a river, and it causes a contraction and a sudden expansion of flow. Whenever you have a sudden expansion and even contractions, you tend to get flow separation. But one of the big differences between diffusion wave and the full momentum or the shallow water equations is that diffusion wave does not account for rotational flow. So you get this kind of idealized pattern, which doesn't look very realistic, especially if you've been out to rivers, right? Right, Tyler and Mike, you guys have seen enough rivers, right? You would go, well, this doesn't look right. I don't see water making 180-degree turns around an obstruction like this. There's going to be some separation and some eddy patterns, right? And so that's what you get with diffusion wave. You get this idealized flow without rotational flow. So this tells me right away, hey, this is most likely diffusion wave. So when we switch over to the SWE full momentum, now you can see we've got our rotational flow. So this would be another kind of visual way to tell in your results whether you've got diffusion wave or the full momentum SWE equation.
Very good. Thanks, Chris. That was a great answer. And I forgot to plug, this is a good opportunity since you brought it up, our next classes that we're offering. We have our 6-week online class that's starting October 9th. That'll run through November 13th. That's a 1D, 2D class. So that's open for registration at this point. If you're interested, go to Kleinschmidt, kleinschmidtgroup.com, and you can find a link there to sign up for the online class. And then the in-person class, we're going to be teaching in Atlanta, Georgia, September 10th through the 12th. That's a Tuesday.
It's going to be hot.
Thursday. Yeah, it's
going to be hot.
It's going to be warm. The class will not be outside.
Shorts. Can we
got
teach?
Confirmation it's not going to be outside.
Can we teach this in shorts? I wonder. Is that frowned upon?
I think we can teach in shorts, but we should have plenty of air conditioning, so I don't think that'll be necessary.
Maybe shorts and our t-shirts with the Runmans on them. Yeah.
And in addition to that in-person class in Atlanta in September, that will also be connected to our annual HEC RAS Pub and Grub. So we're going to have that, I believe, on Thursday evening. So if you're attending the class or if you're in the area and just want to join us for a night of RAS presentations and beers, look for more announcements on that particular event coming up. So, next question from listeners here. This is an interesting conversation. I don't know necessarily if we have a good answer, but it's a good conversation to have. So this person is running a very large model with a few 100,000 cells. They have 17 different boundary condition input hydrographs. So a lot of different inputs, probably a very flat system, a lot of different flow and a lot of flow quantity. And they're trying to run this over the course of a 12-day simulation with a half-second time step. And when they go to run this model, the program, the quotation here is the program does not simulate, so it doesn't complete the simulation. The solution they found is to divide the model into 4 3-day simulations instead of 1 12-day simulation, and that seems to work. And they're wondering, Chris, what could possibly be going on here? Anything jump off the page to you?
Well, the first thing that jumps off is 110,000 cells is not particularly large. I mean, I would call that maybe a medium size. I try to keep my cell count below 100,000 if possible, but if I go over, I'm not too freaked out about it. And it certainly is not the kind of thing that would cause your model not to run. I mean, we've had models of over 1 million cells before, and they run. It just takes a while for them to go, right? So it's likely the 12-day simulation side of things. It's the length of the simulation that you're trying to run that's playing a part in this. Breaking it up into 4 different models is an interesting idea, and kind of adds, to me anyway, adds a little more of my confusion as to why this would not work, because I don't want to say it's not a memory issue, but the fact that you got it to run it with 4 separate models means you probably have enough hard drive space, but maybe there is a RAM issue on the memory side of things. It could be some of your scratch files are getting too big. And so I would check to make sure your resources on your computer are sufficient enough. You've got lots of hard drive space. You've got plenty of RAM, and as we always say, don't run it off your network either. That's just especially with a big model, your network drive. Run it right off of your local drive if you can. Or if you've got a remote computer. We've got a nice remote computer we can dial into that works really well too. But running it off a network, you're asking for trouble, and that could very well be the problem here too.
Yeah, it's possible you lose connection at some point during that simulation. The first thing that comes off to me is this is kind of an issue that we run into a lot of times with questions from listeners, and that is not given a lot of information in terms of what exactly is happening at the end of the model. So the description here is that the model does not simulate. That could mean a lot of different things. You know, does the model crash? Does the model restart? So when you open it, it's closed. Does the model run, but it doesn't post-process the results? A lot of different potential outcomes here. And so this doesn't necessarily answer the question, but I do think it's a good reminder for everybody who's listening. And that is, if you're looking at the results of a model simulation, understanding how the model doesn't finish can be really helpful for diagnosing what the problem is. Because again, if the model crashes due to instability, that will lead you down one direction of troubleshooting. If the model just closes out and restarts, that will lead you down another path. If there's a memory issue, oftentimes you'll actually get some output that specifically calls out that the model or the computer space is running out of memory. And so really pay attention to how the model is not completing, and that can help you not only ask better questions, but also to potentially self-diagnose a little bit better what's going on.
Yeah, I mean, look at the compute messages. Now this one is a nice stable model, and in fact, it's so stable, I just tried to run it at a 1-hour time step and it worked. So go figure, right? I was hoping to get it to crash so I could show you some error messages here. But when your model does crash or it doesn't run, look through here. The messages are not always that helpful, especially when you start getting the red text. You get these unknown kind of Fortran-y looking computer code errors, and that doesn't help us out too much. So look in between that. Look for keywords. Look for something that can kind of give you a clue. There's usually something in there that you can use to at least kind of steer you in the right direction as to figure out what's going on. So
yeah, and even if you can't understand the text, at least you can include that text in a question if you're asking for technical support from somebody else.
Yeah. Yep. Absolutely.
All right, last question here before we dive into the primary topic for today, and that's a follow-up on the river restoration 1D versus 2D episode that we had last month. Robert Schomp, who we had as a guest for that presentation, was sharing an approach that they used for modeling river restoration sites with 1D models. And for those sites, they ended up using blocked obstructions to simulate some of those restoration features and the effects that those would have on upstream cross sections. And the follow-up question here is, would an ineffective area be more appropriate instead of a blocked obstruction for doing 1D restoration modeling? And what would kind of the pros and cons of each be? So Chris, you want to give kind of a 10,000 foot overview on what that would look like?
Yeah. So first of all, if you have a 2D model, you don't have to worry about ineffective flow, which is one of the great things about 2D models. But we're still doing 1D modeling, and they still have their place for sure. And when you've got a 1D model, how do we take into account water that's not moving in the downstream direction? In other words, two-dimensional effects, right? So you get water moving laterally, or in the case of an eddy pattern, you might actually have water moving in the upstream direction. Well, any water that's not effectively moving in the downstream direction has to be treated as ineffective flow in RAS. But we also have this thing called a blocked obstruction, and they're kind of entered in the same way in RAS. They look similar in how they're represented, just the color is different. A blocked obstruction is black, and the ineffective area is kind of a green hatched color. So they are sort of similar in a lot of respects. Now, the big difference is an ineffective area allows water to be inside of it. It just doesn't treat that water as conveyance. So it's not actively moving downstream. What it is treating it, though, as is storage. So when you have an ineffective flow, that water in there is part of the storage term in the full momentum equation. Okay. Now, a blocked obstruction is exactly that. It's just completely blocked the area out. So there's no water in there. So it's neither storage nor conveyance. Now, when you have a steady flow model, there is no ineffective, other than taking away from your flow area. There's really nothing done with the ineffective. It doesn't deal with storage at all. Storage is only a part of an unsteady flow analysis. And so if you're doing a steady flow model or quasi-steady, an ineffective area and a blocked obstruction are almost the exact same thing. Now, the only difference between them is how they treat wetted perimeter. An ineffective area does not count the wetted perimeter, or does not count the perimeter under that ineffective area as wetted perimeter, whereas a blocked obstruction does count that as wetted perimeter. So that can change your answer slightly. But if you're doing a steady flow model and you go, all right, I'm doing this as an ineffective area over here, let me switch it to a blocked obstruction and see what the differences are. It'd probably be a very slight difference, but not much. But when you get into an unsteady flow simulation, then they're going to have a very big different effect on the attenuation of the flood wave through that area. Blocked obstruction does not store water, so it has no effect on attenuation, whereas an ineffective area does. It is counted as storage, and so it will attenuate your flood wave more.
Yeah, so you'll end up with a higher water surface elevation if you use blocked obstructions than if you use.
Yeah. So that was, sorry about the long discussion, but the question here is actually which would be more appropriate, I'm assuming, for river restoration. And so hopefully having that understanding of the differences can answer that question for you. But I see a blocked obstruction as being a more conservative way to represent, say, something like a log jam, because you're blocking the whole thing out, right? Especially in a steady flow type of model. You're blocking it out. You're going to have more flow getting pushed around it. So you're going to have higher velocities around the perimeter of that structure, higher shear stresses. You're going to have more head loss upstream as well as a result. So it might be a more conservative, but maybe not quite as accurate, because these log jams will have some water inside. It will have some storage. And so that's how I think of it.
Yep. Good. Yeah, no, that's a good answer. I don't think that there's, like as with most things with hydraulic modeling, there's not a clean answer. Just a matter of kind of understanding the limitations between the two things.
And that's a really good point, Ben. It's like I almost put more value in answering this question in the description of the two different features, because that arms you with the knowledge needed to make that decision yourself, because every model is different. Everything's going to have its own kind of unique situation and circumstances. And so understanding the differences will help you make that decision, instead of us just giving you a blanket result for which is better or more appropriate. Yeah.
Yeah. Yeah. And that's a great transition into the Nature Like Fishway rough and channel discussion, because there are quite a few parameters and decisions you have to make as a modeling user with how you're representing certain features within a Nature Like Fishway. And there's not necessarily a right way or a wrong way to do that. Most important to understand what the impacts would be on your model, so that you can, quantify the uncertainty and, what the results of those assumptions might be. So anyway, we'll get into that a lot more here in a second. Before we transition into the main topic for today, I'm just going to do a quick little ad read here. So we are grateful to be sponsored by our firm Kleinschmidt Associates, who is known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more at kleinschmidtgroup.com. You can also sign up for our 1D, 2D HEC RAS classes at kleinschmidtgroup.com. And you can see some really cool Nature Like Fishway project examples on our website as well. I know we got some cool visuals and descriptions of some of those projects up on the website. So a lot to learn there if you're interested in doing so. Let's go ahead and transition. So again, reminder, our main topic for today is kind of everything around Nature Like Fishways and roughened channels, including the name difference between those two things, which we're going to get into here in a second. But I thought it'd be helpful, maybe, Tyler, if we could start with a brief overview on kind of the history of Nature Like Fishways, where these came from, how we got to the point where we're at today in the industry of using these for fish passage solutions at different projects. Sure.
Yeah, so some of the slides I'll be sharing here were from our 2-day Nature Like Fishway workshop presentation. Those slides are published online, and so we can include a link in that with the vodcast, but I'll just go over very briefly a small portion of that and talk through that. So just want to acknowledge that since pre-colonial times in North America, people have been modifying river systems more for the harvesting of fish. As you can see here in these graphics, there's such thing as an eel weir that's found in the Susquehanna River for out-migrating eels to funnel them into a basket so people can harvest those at low flow. From that, then moved into just acknowledging the 17th century in France. They were working on some sort of a salmon ladder, trying to support that population and getting upstream. Heading into the 18th century back in the U.S., the Plymouth colonies passed a law prohibiting weirs across rivers because they realized the rivers were important to fish. And so that was on the books initially. I think industry took over and the dams were built anyway in some cases. But they did at least recognize that these seasonal migrations happened. And then we come into the sort of the 1800s, early 1800s, and the cod ladders. Again, this is for fish harvesting, not necessarily for passage, but you can see how the fish may have swum up this modified bypass system, and they would be people with nets in each one of these pools harvesting fish for consumption. So it was primarily about eating the fish instead of saving the fish in this period of time. In about the 20th century, Gustave Daniel published a paper and some information relative to a Daniel fishway, which is what we think of as a technical fishway. And that really expanded throughout the 20th century with some of Milo Bell's work related to these technical fishways. And we think of technical as ones that have a lot more concrete and steel as the basis. Although some of us would argue that a Nature Like Fishway still is a technical fishway, just a little more nature-like. Sure. So then in the 20th century, a lot of it was about sort of the concrete and steel, ice harbors, vertical slot fishways, fish lifts, where you put the fish in a hopper and raise them up 80 feet above the dam and dump them above the dam. But then there's more recently been a turn back to some of the nature-like fishways where you're actually mimicking the natural system, but it's still a hydraulically designed structure to provide suitable depth, velocity, and characteristics that the target species can pass through. So that's a little bit of the history of nature-like fishways and maybe how they were originally used for harvesting fish and modifying rivers to where we are today, where we're trying to often bypass a dam or a road crossing or some sort of a barrier. It could be a perched culvert. You just need to reconnect the stream and provide passage at.
So, and as I ask this next question, Tyler, I don't know if you can pull up an image to show the audience what a nature-like fishway looks like compared to maybe one of these more kind of hard infrastructure fishways. Sure. Mike, my question for you is, the transition between more of the hard infrastructure fish passage solution to more of this nature-like fishway or roughened channel solution, was that made because of actual efficiencies in or effectiveness of those more nature-like fishways? In terms of actually passing populations, or is it more of a visual thing? Like, what's the driver behind kind of going in that direction?
Well, there's definitely the visual thing for us humans, but I think it was our understanding that these natural steep streams that we were seeing very small fish of all different species migrate up in nature. These streams were doing better passage than our technical fishways, and they were passing many different species and life stages. So it's that complex hydraulics that the Nature Like Fishway creates, the micro hydraulics, the substrate at the bottom, making very low velocity zones that small fish can move through, versus these concrete fishways where it's fairly uniform vertically what the velocity distribution is. So trying to create those nooks and crannies for all the different fish is where I think why we moved to Nature Like Fishways, besides the aesthetics for us humans. So
sure.
Yeah.
Now, if we recognize that they're better looking and maybe they're more efficient at passing multiple species, why not just do these at every single project? What's the big setback there, or what's the big limitation in terms of implementation?
Yeah, no, there's definitely one. The slope that they work at. So that, at the upper limits, I mean, people push it, and fish can go, salmon do go up like 10% slopes for a while, such, but generally we're limiting our slopes on our Nature Like Fishways to 4 to 5%, and it really depends your context. If you're in a big river like Tyler's in, is that those slopes are crazy.
We're like 1.5%, so you need a lot of real estate.
Yeah, so it's just about real estate, and now do I have a big switchback and I have to have this channel go S turning around, and it looks kind of out of context with what you're building, and you don't have the real estate, so, and the cost goes away. So a lot of things to think about. Technical fishways definitely have their place. It's kind of a toolbox, and the right tool for the right project.
So I love modeling Nature Like Fishways, roughened channels. That was one of the first things I did when I came to Kleinschmidt, and I worked with Tyler at the York Haven site. And one of the first questions that came up in our early on discussions was, hey, can we model this in HEC-RAS, and how do we do that? And I had never done anything like that in HEC-RAS in a 2D model. But I thought, based on my experience, I think we can do it. And so we went through, and it was a challenge, which is why I liked it so much. And we got some really good results. But so, what goes into the analysis side of things? I mean, HEC-RAS is just one piece of it, but how do we know that this thing's going to stay in place?
Maybe, Chris, before I jump to that a little bit, I'll just share a graphic of sort of what a constructed fishway looks like, and then a little bit of the RAS side as well to orient the viewers. So this is a fishway here that we completed last year. And at first glance, you could say, oh, this just looks like a riprap channel. But this was actually all upland. In most cases, portions of it were connected to the river before. So just gives you a sense of what sort of a naturalized system can look like. This one is just being opened up. That's why some of the water is so turbid, but you got all these boulder protrusions. This one was more of a roughened channel style. So you got sort of a quiescent pool area with a riffle at about 2.5% slope. And so that's sort of what we're looking at when we're talking about the actual constructed side of a Nature Like Fishway. If we think about sort of the why, I'm going to switch to an aerial image here on that York Haven project that you mentioned, Chris. And so this was a dam where water's flowing from the head pond here towards the tailwater, and there's no fish passage on this dam currently. And so we said, hey, we need to create something that allows water to flow around it, and hence the fish to swim upstream. So what we did is we came in, this is the existing terrain, pretty high system set up there, and we cut into that a fishway. Now this fishway is a little bit more of a pool and weir system. So you've got water flowing in from the head pond, coming over the first weir, enters the large pool, and then comes down a series of weirs. And this one actually switched to a bit of a hybrid system with a roughened channel and some zones of passage at the downstream end. But that's a little bit what a bypass fishway can look like. Sometimes you've got where your whole road is crossing your river, and you just need to put your fishway the whole way across the river. In this case, this is the Susquehanna. It's a relatively large river, so it went with a bypass. That bypass is still 120 feet wide. You can put a Nature Like Fishway on a small stream, something that's 10 foot wide. You can get a Nature Like Fishway to connect back a culvert or something that's perched and provide that aquatic organism passage. So that gives a little bit of the context of what type of fishway a fishway, Nature Like Fishway could look like, both once it's built and in the modeling scenario. So.
Yeah, that's great. And I think that picture in particular highlighted the point that Mike made in terms of, that's a pretty flat slope, right, between upstream and downstream compared to, some of these higher head dams, right, where there's quite a bit of difference in elevation, and you'd have to have an amazing amount of area and length to be able to have those slopes be passable for fish. So, Chris, do you want to re-ask your question? You had asked.
Yeah. So, my interest, of course, no surprise, is how do we model this, right? Um, to me, it's not a 1D model. There's really no chance of that unless you're doing something really, really basic, right? And a 2D model seems more appropriate, but maybe not even tells the full picture, because you can imagine in something like you showed, Tyler, there's a lot of vertical acceleration of flow. You're not going to get in a 2D model, the 2D HEC-RAS model. So I'm interested in, what is the process? How do you go about designing this so we can make sure not only is it going to pass fish, but is it going to stay in place for a long enough period of time for its design life? What's the process there? And while you're telling that, I want to just show a video real quick of some of our earlier modeling in HEC-RAS 2D of the York Haven, just to give people a flavor of what that looked like. But yeah, what do you guys think?
Yeah. So I think it starts out with some of the design criteria and what's your design case. Some individuals are okay with a little bit of movement in their fishway. If it's not protecting critical infrastructure, you can acknowledge that some of the rocks may move, and that's okay. You may have a sediment supply that's suitable, and you can just let that sort of replenish some of your rocks as it comes downstream. In other cases, you need that thing to be bulletproof up to the 100-year flood and beyond. So I think that's some of the setting of the design criteria. I think coming from a world where I've dealt mostly in 1D models in my undergraduate work, just even having the ability to do a 2D model was awesome, and it gives you so much more visibility into the variability of flows and depths across the cross section. And I think that's where a lot of the guidance right now is at, for fish passage at least, is related to sort of your depths and velocities for target species. And so that's often what we pull in as part of our design criteria system there. And yeah, I don't know, Mike, any thoughts you have on?
I think, and you've got that one graphic of kind of that design process, Tyler, but, really I emphasize with everyone I work with here is don't start with a complex model, but really start with you're at a cross-section analysis. And then we have these empirical equations for Manning's roughness coefficients. And so run different shapes of cross sections for your roughened channel, and then use the Manning's empirical equations to estimate what that roughness could be. Size your boulders. Here, got this.
I can jump to that graphic.
But yeah, I mean,
in a bit, but yeah,
here's like the standard equation from the core. This is often where we start with our sizing our rock, and then we have some relationships because our rock mix is going to be much wider gradation than what the core uses for a standard riprap. So
yeah,
our D84 is going to be, in this case, 1.5 times what the core equation gives us. And we make a gradation, then that goes into that Manning's roughness equations that use grain size. And then that goes into getting us a Manning's N that goes into our single cross-section analysis. And we kind of iterate on that scale because it's fast. You can do it in an hour. And then we can start to, now we got to start grading in CAD and make a surface. So that's why we really want to work it out in that single cross-section analysis, the first few steps.
It almost seems like it's a real balance. It's almost, you have like, your standard like scour protection calculations, right? Where you're coming up with the size of riprap that you need to stabilize a bank or to protect a bridge abutment. And then on the other side of things, you have like a stage 0 restoration project where it's all about just, putting in certain features to return a system to its natural kind of physical processes, but you're not super worried about, things changing or moving. That's kind of part of the whole deal. Nature Lake Fishway almost seems like it's kind of bridging both of those options where you have hard engineering aspects where you need certain things to stay or certain things that are sized to protect, but at the same time you kind of have to or want to have some of those natural processes occurring within your design. Is that right?
Yeah, and I think from my perspective is like, so this is step one, but then the art of it and using nature to, and the simulating nature piece of it is the next step, which is now I know the rock size I need for stability and for roughness. Now I gotta start making an arrangement. And that's where the fun part is like, how am I going to arrange my big boulders? I call them structure or frame rock boulders, to give the flow patterns I want for the type of slope and size of and flows I'm working with and the size of the channel. And kind of figure out, am I in a kind of a chutes or rapids and pools? I'm doing like a step pool system. What is it that I'm building here?
Sure.
So.
Tyler, do you want to go ahead and share that figure
Yeah.
that kind of goes through the Nature Like Fishway process so people can kind of get a better understanding of what that looks like at a high level?
I think if that's coming through, yeah, it's a good reminder, Mike, of that sort of sequence of what a Nature Like Fishway design can look like that we presented at the one-day workshop here. So we start out with this system that's got a problem. What is that problem? Well, it's generally fish passage. And so we think about that and we say, okay, let's develop some design criteria. What are we going to do? What are requirements to get fish past this barrier? We gather some data. That's sort of an iterative process, thinking about risks and what you might need for permitting. Once you got some data, then you can start thinking about alternatives there, okay? Is a Fishway the best option? Are there other non-Fishway solutions? Dynamite might be involved. You might just get rid of the dam. You might truck the fish up and around it. Truck and transport is a thing where people not harvest, but collect the fish and move them upstream above the dam. And it may be not 1,000 miles, but 100 miles or so upstream. Might just be literally just around the dam abutment, and that's cheaper than building a Fishway. But if a non-Fishway solution doesn't work, then you think about, okay, what type of Fishway works? Again, considering risks and cost. Maybe you need to go back and gather some more data. Considering the type of Fishway, it might be there's a non-Nature Like Fishway solution. This is those technical Fishways we talked about, a little more concrete and steel. Certain situations, those are very appropriate, particularly high head. But if you conclude that a Nature Like Fishway is the correct one, Mike, as you acknowledged, then you start thinking a little bit more about the local geomorphology. Is a step pool system a little more appropriate? Is more of a roughened channel with a large riffle and then a larger pool below it appropriate? And you take that into sort of this initial pick a slope, pick a cross section and run it in this 1D, not even 1D, an Excel calculation almost, where you're really just trying to understand what's going on preliminarily and get your ballpark width and slope set. You might have a constraint. You say, I can't go more than 500 linear feet on this Fishway. And so is my slope even suitable for this species? How many boulders do I have to think about putting in there? What roughness do I need? Take that slope and cross section then and throw that. And sometimes you might pick a slope and it may say, hey, we need to go back and gather more data. You got to go back to the drawing board. Maybe you can go ahead and go on to hydraulic modeling and do that first sort of best case scenario. You take that into your hydraulic model, you develop a reasonable hydraulic model, check if that meets your criteria for your given species, check your costs. As with any good project, keep an eye on cost throughout it. And that may require you to do a stability check at that stage as well. Mike, as you said, checking your rock size. Can we get that big of rock locally? What sort of gradations are we talking about? And you sort of iterate in that slope, cross-section, hydraulic modeling, criteria check, stability check for a while. And sometimes that may require you to go back and pick a different type of Fishway if you can't get a solution to work out. Just like if that model doesn't converge at the end of your run, you know something's wrong and you need to go back and see which parameters you need to tune. Sometimes you got to go back and even ask, is the Fishway the right type? And sometimes you go the whole way back to your design criteria and say, maybe this design criteria just needs to change. We had one Fishway that required us to have a narrow notch for low flows, and it was just causing us headaches. And we went back and said, we're just going to strike that. We talked to our partners and acknowledged that's what we needed to do to make this function. But once you get out of that, once you check all those boxes on cost, criteria, hydraulic model's good, stability's good, only then do we think about sort of the design drawings, and then to follow on the detailed costing and risk assessment, and then get into permitting. But that's sort of the life cycle. But there's a lot of iteration there in that slope hydraulic modeling. I mean, I don't know how many Yorkhaven runs we did. I mean, it was probably 30, 40 runs of like detailed 2D hydraulic models that we were running. And that one, we did have a pretty good idea what we wanted to do, but it was, hey, tweak this, modify this, let's see. So getting that first start as good as you can is really helpful. As Mike acknowledged there, start with just a simple Excel equation for a Weir equation. How much flow can I get across this flow control structure? What does that look like? So.
Yeah. So you can see this is a great figure, and kind of thanks for stepping through that with us, Tyler. It obviously, this is a very complex process, requires a lot of iterations, a lot of probably multidisciplinary input from different team members, and just thinking about and seeing some of the hydraulic modeling that's done for these types of things. One question that pops to my mind is, can we get what we need from a 2D model to answer these types of questions? Particularly because, as we all know, the 2D output is a depth averaged output. So basically you have a single velocity throughout your water column. That's the assumption that's made within 2D modeling. These are very three-dimensional cases in many situations. And so, Mike, I guess throw it to you first. Do you feel like 2D modeling is adequate in many of these cases? Is there a need to do 3D modeling, or is that kind of the direction things will go as computational resources become, more available?
Well, I'm sure it'll go that way once we have those resources, but at this time, I don't think we have those resources for the size of the projects that we're modeling. And I'm not sure if we know, even with more information, what we're lacking, I think, is really the information on the fisheries, the biology side. A lot of times, turbulence, we can go into that for a whole day, and what, disorienting the fish and all that. Also, when we start talking about fish that are a quarter of the size of your cells in your model, how accurate is it going to be no matter what? So I think for larger fish, when you're modeling in a 2D, I think it gives you a fairly good answer. And also thinking a lot of these nature-like fishways, I think as we saw the earlier example, the fish passage flows that we're analyzing, they're typically below the top of the big boulders. So we're not having like streaming flow over the top of the boulders and a flow separation vertically, but rather we're having more of a contraction, expansion, jet and wake flow. And maybe the 2D model is pretty good for that. Some of the validation modeling and field measurements we've done, I think it shows that it does do quite well with that type of flow. So
is it common to take this, or are you aware of any projects where it's gone to physical modeling?
Yeah, we've done a couple physical models with Northwest Hydraulics up in the Pacific Northwest. They built it for us, and we're working with them on the designs. Here I could share like one example. And I learned probably more in physical modeling and playing at the beach with streams and stuff than I did with any type of numerical model, because you really feel it. This is an example, a rock layout. This is actually for the physical model for one of the sites. This is on Trabuco Creek in Orange County, California, where they still actually have large steelhead sea run rainbow trout. And so this shows the kind of the large structure rocks, ABCs, their layouts and pools, and this is basically chutes and pools. And this is kind of the physical model of it. It's a 1:6 scale we did. They built it. And then myself, Ed Wallace with NHC, we moved the boulders around, turned back the water on, do it again and again and again. And we really rearranged the whole layout after playing with this. And tried to make one of the shoulders, the edges, higher than the other. So when we found that when water would start to go over the top of the biggest boulders, it would start to stream. It probably wasn't good conditions anymore for large steelhead to go through. So we really wanted to always have areas that had big boulders sticking out all the way up to our high fish passage flow. So here's kind of some of the runs.
So what was the trigger that actually made or allowed you all to do a physical model? Because that's not a small undertaking. So kind of how did that come up?
It's a large scale project, and there was a lot of different entities and owners that had a lot of questions. So and as well as we had another physical model in the same lab of the entire project. So this one was really focused on the roughened channel, but the bigger one was full the entire project area. And that really gave a visual, hands-on for those that really need to approve the project as well. So it served both hydraulics as well as a little bit of public relationships, building trust in that it's going to work.
Are those the weirs that you have in the middle there? It looks like they're made out of wood. Is that a permanent feature in the final design? Yeah. And is that a common thing to do for these?
It is. It was, in this case, it was these weirs, concrete weirs that were going to be in between to be able to control very low flows. So kind of similar, like Tyler mentioned, like we were, had to pass fish at 3 CFS. So it was, yeah. And then
you got to get that concentrated.
250 CFS on the upper end. So it's a huge range. Yeah. And then here's another one we did. I'll just real quick, this is a similar, different lab by NHC, but same river system, another Fishway. So different flows. So this one was done during COVID. We couldn't go to the lab. It was kind of not nearly as informative because I wasn't there to be hands-on and move boulders around.
Yeah. Mike, did you invite any of those stakeholders into the first example when you could go to the lab? You could actually invite them in and say, hey, this is what it'll look like. Did they appreciate that?
Yes, and we actually, as part of the project, we actually flew them up to the lab and walked them through, did move things around for them, put debris into it. Yeah, it was very hands-on. And then this one we did kind of a video, kind of live stream with them. Yeah.
That's something I think us engineers sort of forget about sometimes, is the public relations piece and how valuable that can be to sell a project or convince somebody this is going to work when they see it physically modeled. A 2D model is good. We understand that and can read it, but some people just need to see that flowing water.
Yeah. Well, you guys have seen those sand tables, right, at conferences? Mm-hmm. It's like a giant sand table, and they all get to play in it. So how fun is that, right?
Yeah, that's very, very, very cool. Thank you for sharing that, Mike. Yeah, that's a great kind of another option, right, as you're trying to wade through the different design criterias and the way to sell these types of projects. That physical modeling could be a really interesting component. And I liked your thoughts on the kind of the 2D, 3D comparison and how where we're at right now, 2D is probably adequate in many, many cases. I'm going to turn it over to you, Tyler, for a follow-up question on that. And that's about, something that we run into a lot of times, which is people using 2D modeling by default just because it produces results that are more visually appealing. But in reality, in many cases, doesn't necessarily actually give us better results than just a typical 1D model would. So in your opinion, I don't know if you've actually done nature-like Fishway modeling in a 1D model setting, but do you feel like, the 2D modeling and the results that we get from that we're almost tricking ourselves in terms of like the amount of detail that we're getting from a modeling solution like that, when in reality, so much of the work that goes into the nature-like Fishway process, like you mentioned, is just kind of simple spreadsheets, right? And just computing kind of some of these high-level design estimates or boulder sizing, and then just taking that out and making it happen. Do you feel like 2D is still a necessary piece of that puzzle, or do you think we can probably do more with less?
So I think there's been a lot of things that have been designed based on Weir equations and one-dimensional analysis for many decades, and I would say that is still very valid. I think where 2D has its strength is as we start to think about individual fish species, and is this fish going to swim in the center of the channel or in the edges, and really selling that to the stakeholders that care about that fish. It shows a spot for that fish on a map. You can literally plot on a map, this depth and velocity is suitable for this river herring to go the whole way from the tailwater up to the head pond on a map, where 1D, you're left with a cross-sectional average, and yes, it should work based on experience, but you can literally plot it on a map. And we've got enough biological data now that I think we know depth and velocity for most of our target species that we care about, or some surrogate can be picked that you can sort of understand biologically where that fish may swim, or best we know. So I think 2D does offer a valid use in a nature-like Fishway, but I still think with that initial Weir equation and Excel calculations is where you start, and hopefully take out a lot of your runs. Because if you start with a 2D model right off the bat, unless you got a really good CAD person and somebody who's really good at HEC-RAS, you're spending a lot of time and effort iterating early on, when you should just be on a Weir equation basis and just go.
Yeah, and I know you've got some good examples of routing fish. This is just another one like that. So this is what a lot of our reviewers want to see is this is like hydraulic a run at a fish passage flow for salmon through a culvert in a roughened channel, and just a traced determined route there in the dash line of where the fish could swim that gives it good depth and velocity conditions, and then we can plot those depths and velocities along that path, so they can see, maybe we're not meeting criteria every little spot, but you can kind of get the sense, okay, there's a little peak in velocity somewhere. Well, people that know that fish, they're like, they'll make it right through that spot.
So
how
I think
big
this
is that
is
culvert?
Oh, go ahead, Chris. Yeah.
I was just wondering how wide that culvert is.
14 feet for scale.
Okay. Oh, cool. Okay.
It's a box.
So I think this discussion on like utilizing the results from 2D, which I agree are very visually appealing, but also like important in terms of like telling the story of how this is going to work for fish that are experiencing the Natrec Fishway roughened channel. Of course, the follow-up question is how do we know that those results and the figures that are being generated are representative and real once this thing gets built? So I want to transition to validation and calibration because I think that's a natural connection here. So Tyler, I'll start with you. In your experience, how have you gone through the process of validating or calibrating those modeling results that you're using to tell a story of how this thing's going to function?
Yeah, let's see if I can find a slide here while I'm talking. But oftentimes you do all you do the pre-work, the data gathering to get your head pond and tailwater, come up with that and try to understand what's going on in the system. And then use that to build your model. And of course, we all think the model is absolutely right until we prove it's not by doing the actual construction and show that it doesn't behave like we thought it did. And that's why going back out and doing that validation is so important. Let me see here if I can kick off a slide set and get back to share this. Oops, not that one.
No rush.
And let's see here if I can get down to that. Just talk about this a little bit here. That should be coming through. But yeah, that hydraulic verification piece is critical because if you're knowing that fish can swim at a depth and velocity, yes, that might be the general average, but your fish in your region might be smaller, they might be larger. There might be certain things that just you don't recognize. And so you either do, well, you do two things. I'll say the first is this hydraulic verification, where you actually go out with an ADCP or a Marsh-McBurney or a pygmy meter and take some spot measurements, take a GPS point, take a spot velocity and depth, and see if it matches up well. This is the Fishway that we did on the Susquehanna, the one that was constructed last year. And this is all the spot measurements we took at depth and velocity. ADCPs can be challenging, especially if you get a little bit of turbulence. Some of these systems don't do well on that, but you get the best data you can for that system. And then you come in and run all that through there and get these sort of comparisons. On the top here, we've got a design case with green being passable for river herring. That's what we thought we were going to get. And we've got the as-built condition, a little bit less green, but still identified those passage zones and worked through some of that. So yeah, it's definitely worth doing. And if you build it, everything sounds great in the model. And as I indicated earlier, everything sounds perfect until you actually think about actually constructing this and where do your riprap tips actually stop relative to your smooth surface that you're modeling. Do you put the boulders in the terrain or not? I know Mike's got some experience with that on the backside, but I'll just close with this. The second portion there is you can also just test the fish. You can literally go in and tag the fish and see if they swim up through the system or not. There's mechanisms to insert a tag in a fish and then see if it swims through the Fishway, and you can detect it upstream. So that's sort of the other way of verifying that it meets your needs beyond just the hydraulics and comparing that.
Tyler, what was the key takeaway here in terms of lessons learned between the design and the as-built condition? Because as you noted, it looks like based on the data collected that you went out and got that there is less passable area than what was originally modeled. What were the key takeaways? Was it an underestimation of roughness? Like what was the key change there?
bring this photo back in. And so the key takeaway here was in your as-built, it's really important to get the contractor to understand where your grade is, and also for the HEC-RAS modeler to understand where your grade line is, because your riprap is going to vary up and down by 6 inches low, 6 inches high. Do you want your design grade at the bottom of that at the lowest point, or do you want it at the tips of the riprap or somewhere in between? When we did the as-built survey on this one, they used the drone to get it, which was great. We got great coverage and could see all the boulders, but it did mute out some of the low points that were missed by the drone. And so our surface was slightly higher than we had designed it as. So you'll see in this case here, this green that we had on that fringe, we thought we were going to get a lot more shallow habitat for this species. That sort of creeped in a little bit because our terrain was shot a little high. So a big lesson learned for me on this one was making sure that your contractor and your hydraulic modeler and your construction staff that are supporting it in the field, building it, understand where that design grade is and make sure your as-built can capture that accurately as well.
Very, very cool. Mike, do you have any additional thoughts on other validation or calibration methods that you've maybe used on HVAC Fishway rough and channel projects in the past?
Yeah, I mean, we've just kind of started to do, validation, or I'd say post project and evaluations. A lot of our modeling up till very recently has been, just a graded CAD surface and then putting a big Manning's ends in. So you're not getting that flow diversity in your model results and everything else. You're checking the depth and kind of really just an average of velocities. You're not really getting what the fish is really going to experience. So we're starting to put in the boulders into our surfaces like Tyler has. It's a lot of work. We tried using cylinders in RAS. Those work to some degree when they're sticking above the water, but then at the same time, you can't put them together and make that little notch that boulders when they touch make. Really tricky. We're really trying to find a faster way of putting boulders into our surface that protrude like we usually want them to protrude about a third of their diameter above the surface. So, those that have tricks for that, I'd love to hear. We're trying different things. In terms of validating, and we were trying to understand how much the boulders in the surface matter, which we know they matter a lot, but how much they matter and how much they influence our Mannings. We kind of did some validation. Here's one of the sites. This is the one I was just showing, that box culvert, 14 feet wide. Fun building this rough and channel pools and chutes inside a box culvert.
Wow. Yeah.
Glad we can put the top on as you're building it. So it's
no kidding.
Still. And then so let's see if I can advance it here. So what we find is they initially the as-built conditions that they haven't got any flow on them yet, and so there's the surface hasn't really evolved to what it's going to be. The fines haven't washed out and shadowed and everything. So this stream was lucky enough that it goes dry in the summer. I guess that's unlucky, but lucky that we could go scan it the next summer. So this is we scanned it and got basically a LiDAR, ground-based LiDAR scan, made a surface of it. And there's our surface of it here. We compared it to our design graded cross sections, which was pretty close. You can see all the lumpiness of those boulders. We're pretty good there. And then we had a couple high flow events. This was one of them where we went out there and we took velocity and depth and water surface shots all over the place. We also did LSPIV, which is with video tracking bubbles on the surface to look at surface velocities as well. But here's kind of that. Those are all the points where we took velocities in the water, 2/3 of the way of the water column, and we have water surfaces. And then we put a model together and tried to calibrate the Mannings to that. And we, here we had 0.06, 0.08, 0.1. This is the residual error between the observed and the modeled. And so, it's not bad, but still, we're off by 0.4 feet here, plus or minus, but, generally 0.2 plus or minus. But the ends didn't matter all that much because now we had that surface roughness kind of in the model. Was a lot less sensitive to what end we used, we found.
Yeah, I think that's a really, really important thing that you just brought up, Mike, for the listeners and watchers of this podcast to understand that those end values you have posted there, they are highly dependent on not only the flow rate we're looking at, depth of flow, fish passage flow versus flood flow, but also how you're treating the boulders and the other rough elements in your model. Are they part of the model geometry, or are you lumping them into the end value? Because that can make a big difference on what the end value you actually calibrate towards is. Correct? Do you guys agree with that? Or okay.
Yeah, Mike, you had done some study on that as far as the form versus Mannings and form govern, but you want to say a little bit more about that?
I don't think we have enough to really say a hard number, but I know there's some other work on that as well. I mean, the form is definitely a huge proportion of that, energy loss that's Mannings is trying to represent. So
yeah,
I'd like to see a lot more work on that for sure.
Yeah, I think in reviewing some of the documents you sent us before this podcast, Mike, I think what the high level conclusions were for flood flows, the Manning's roughness coefficient becomes quite a bit more important in terms of what you're selecting there. But for lower flows, the form really drives a lot of what's going on.
It doesn't matter that much, which is nice. I mean, that's a really good thing. Is if you're not as reliant on picking the right end for your fish passage analysis.
Yeah,
because models, if you've got those boulders in it, the model's going to do a pretty good job resolving that energy loss.
Yeah, we have a project that we're doing right now where we're looking at a natural channel and the fish passability of it under different flows up in Alaska. And the analysis that we did, we're spanning from 20,000 CFS all the way down to about 1,000 CFS, so a huge range of flows. And what we did sensitivity analysis on all of our model conditions, and what we found agrees with what you're saying, Mike. At those higher flow levels, the model's more sensitive to adjustments in Manning's N. At the lower flow levels, even at 1,000 CFS, which for this system is pretty low flow, still quite a bit of flow, obviously, overall. The adjustments that we made to Manning's N and to turbulence were very, very, very resulted in very small differences in water surface elevation and velocity. So we've observed the same conclusion that you just described.
And that was with having these roughness elements actually worked into part of the terrain, right?
Yeah, that's with having a high quality bathymetric surface.
Yeah. So, that's a very big distinction, because when you don't have those roughness elements as part of your terrain or part of your cross section, your N value will skyrocket at low flows. To account for that missing roughness, right? That's part of the form. So it gets really tricky, right? Because how much do you work into your model, how much of those boulders are part of your model, and how much is part of the N value, and then that we haven't even talked about turbulence, right? So how does that play into the whole thing here? So it gets really complicated.
Mm-hmm. Yeah, and just like you were saying, Chris, here's your Manning's N. This was back calculating if you don't have the form roughness in there. It's like, this is 1 foot depth in the channel, and it just goes sky high 0.5, Manning's. Never learned about that.
I mean, you see that, and you see that with Jarrett's equation too, right? Mm-hmm. When you're when you use Jarrett's equation in a steep mountain type stream, it inherently, based on how it was developed, it incorporates that roughness, those boulders, into the N value, not into the shape of the channel. So
it's like N is now serving as, like, instead of a Weir equation or a vertical slot, it's an orifice, or flows going through these very narrow gaps and expanding and contracting. You're trying to somehow push that into a Manning's equation.
Let's transition to the turbulence discussion, Chris, because you brought that up. We talked a little bit about Manning's. No, you're good. That's a good transition. So obviously, when you look at some of the physical modeling that you just showed, Mike, as well as I think what a lot of the listeners might kind of view a nature like Fishway to look like, the assumption here is that turbulence could have a pretty big impact on the results of your hydraulic modeling here. But that's just an assumption. So I guess from your experience, Mike and Tyler, is using turbulence when modeling these types of projects important? Should we be using it? What value should we use? What are your thoughts on that?
Tyler, you want to go?
Yeah, this comes down to the what's your end game. So I would say I'll admit I'm not a detailed knob turner. I don't love all the knobs that are actually in HEC-RAS. I like to stick to the basics, and that's why the weir equations and the simplifications work for me. But also the biology isn't there yet to say this fish requires this turbulent value. If you're thinking about turbulent kinetic energy, we don't have the studies yet that say American shad can only handle X, river herring Y. And so there's no criteria to judge against. We can say, yes, this is more turbulent and this is less turbulent. But we're also seeing now some studies come out that say there are some benefits of having some eddies, with controlled eddies, I'll say, with sort of upstream migrating flow patterns so that you see fish begin to grab onto those and use that to sort of dart upstream through some small jets or small openings. So I think it's useful. I would acknowledge turbulence is very important when you have attraction water coming in. I'll share that York Haven example that Chris and I worked here. Let me zoom back out a little bit.
And while you're pulling that up, I just want to make a clarification for everyone listening too. When we're talking about using turbulence in RAS, turning that on, RAS doesn't actually simulate turbulence. It simulates the diffusion that results from turbulence in the river. So when you're looking at a RAS model results, you're not going to see the turbulence like you see just behind Tyler's head there, right? In the model. That doesn't show up in the model, but you get the diffusion that comes from that. And that's what you're modeling. And you get diffusion anyway with the natural equation, even without turning on turbulence. The turbulence is just an additional way to add diffusion into your process if you think you need it. So anyway, sorry.
Good clarification,
Back to you,
Chris.
Tyler.
No, that's good.
No, that's a good thought there. I just generally think of turbulence, and generally in a Fishway, we try to avoid it for the most part. It's something that for a long time people have said, oh, let's not have any turbulence there. We want to try to keep it nice and neat and not sort of have that. I was looking for a photo to represent this, and I'm not seeing one right offhand, but this one.
Mike, do you have any thoughts on turbulence and whether you've used that in the modeling that you've done?
Yeah,
projects.
We haven't. I asked folks in the office too. They played with it a little bit, but we really haven't. And I did see a lot of good presentations at Fish Passage 2024 last week, looking at, they were instead of using turbulence, and this is also people that were studying the fish, they were using slope and velocity as kind of an analog or as a surrogate for turbulence because of the uncertainty around turbulence, and then looking at fish behavior relative to those parameters.
Well, one of the unique things about a nature like Fishway and a roughened channel compared to other RAS type applications out there is the resolution is usually very, very tight, very small, right? You need really small cells. And one of the reasons to turn on turbulence or to include that added diffusion in a HEC-RAS model is when you do have cells that are very small, when you do have a near field model, especially if those cells are small in size relative to depth. So if you've got a relatively deep channel and a relatively small cell, then you start underestimating diffusion without using the turbulence term in RAS. So this is something to think about for the NL nature like Fishway, is because you do have very small cells, but also at fish passage flows, you tend to have smaller depths as well. So
I did find that photo. I'll just share sort of the graphic in a case where turbulence is maybe necessary or very much worth considering. This is the project I showed the HEC-RAS terrain of earlier, but now we're looking from sort of the land out towards the river, and it's a big broad crested dam. You can see all the energy being dissipated here right at the toe of this dam. In our hydraulic modeling for the Fishway, we're actually going to open up sort of this upper little speed bump portion here and let more flow in as some attraction water over in this corner. And to be able to see that water come through there and realistically represent how much energy it has, I think turbulence does have a place there. Because if we go over to our HEC-RAS model, so that photo was standing up here, sort of looking out through here. When we open up that speed bump, we see a lot of velocity coming through there. And thinking about what that does to the system, I mean, there's a lot of that energy gets dissipated right here. And without recognizing some of that energy loss, that carries it on as velocity downstream, which makes for fish passage barriers and other things. So I think there's definitely a place for turbulence. But again, ask your question, what is your design criteria? And if you don't include turbulence, you may be a little bit higher velocity and you may be a little bit lower depth, both of which from a fish passage criteria are like, okay, if you're too fast and you're too, and the depth is influenced, if you're too fast, the fish can't pass. You're conservative by not including turbulence there. Now, if you actually are turbulent, you dissipate more energy, you might have a little more depth, which could be bad for water levels, and you may miss on some of your weir settings, and had those other sort of ancillary effects. But that just is a little bit how I think about it. What is the benefit of putting it on? And so it's a little bit of a sensitivity analysis. Maybe you run it with it, see what that gives you, and run it without it. Sort of like we used to do with Manning's equations. You run a little bit above and below just to bracket it if your model doesn't take forever to run.
Yeah, I think a combination of sensitivity analysis and obviously the importance of the verification that both of y'all talked about with these types of projects, right? Because the verification is going to capture any of the uncertainty that might be included in including turbulence or not. So I think both of those processes are important to kind of trying to quantify turbulence. I think it's an interesting thing because it feels like there's been a lot of research and work done on like Manning's values in hydraulic modeling, not as much on the turbulence side of things. I think generally models aren't as sensitive to the turbulence coefficients that are being used, but it seems like it's just kind of hanging out there and nobody knows exactly when or how or why to use it. So an interesting topic nonetheless. Go ahead, Tyler.
I was just going to say, I think in one of our models, you said it's not super sensitive to it, but in one of our models, I think it did swing the head pond by 1/10 or so. Okay. And for somebody who's generating water and power, that can matter a lot.
Good point.
It also matters for overall fishway flow. If you get 500 CFS versus 450, I mean, that can change a lot of dynamics downstream. So while it may not change a lot, it is something to consider there just as I think there's, like we all acknowledge, there's a lot more research that needs to be done, but it's a risk to ignore it as well. Because we all know it's there. You can see it in the field when you're at these sites.
Yeah, and I think that's why the sensitivity analysis becomes such an important factor there, right? Because then you can present, hey, this is the possible range of head pond elevations that we're looking at. Are the stakeholders that are involved comfortable with this potential range of outcomes? And if the answer is no, well, then we need to do a little bit more research, a little bit more refinement there. If the answer is yes, then no matter what the outcome is, people can kind of be at least up to speed on why there might be some variations in outcome. Cool. Last technical question for you guys on this topic is around fish behavior. So this is a question I was thinking about in preparing for this conversation, and that is, we can use our 2D modeling output to come up with evaluation of what the fish habitat is within our nature like Fishway, whether the hydraulic conditions, depth and velocity are suitable for these different species that are going to be potentially up migrating or down migrating through our project. But when it comes to potentially using these 2D results to actually answer or model fish behavior type of questions within our project domain, what are your all thoughts on the applicability of that? Is it just way too much to ask the model 2D modeling results to be able to answer those questions, or is it possible? And maybe it's dependent on the size of fish. Mike, do you have any thoughts on that?
Yeah, I mean, definitely the size of the fish matters. We can use it for behavior. I mean, you can start from the bottom, the behavior, attraction flow, as we call it, or attraction. So, if you have the flow split and some of it's going through the nature like Fishway and some's not, the 2D model is very informative in terms of like, do you have a stream of water, fast water coming out of the nature like Fishway so the fish can find it? That's kind of a behavioral piece of like, they need to find it. They need to feel like that's where they want to go rather than try to go over the weir, the dam. So that's where it's very useful. Eddies, recirculation patterns. I think that can be really useful. Large recirculation patterns can be bad or good depending on the size of the fish and the type of fish. So working with a biologist, I think, is really good. A field biologist that knows and a fly fisherman that knows how the fish move around and where they use, what they use, and they could look at the velocities patterns too and tell you something. But behavior is a tricky one. Each species and life stage is going to be different on you.
Tyler, have you used any of the output from some of the modeling that we've done on Nature Like Fishways to analyze or assess fish behavior, or has it mostly been on the habitat and kind of passability criteria?
Yeah. So I think the fish behavior, I mean, obviously we can't think like a fish, but some people have tried and created what they call an individual or an agent-based model. So with the agent-based modeling, I think there's some benefits there that we can start to think like fish. You can program a fish with a range of characteristics as far as velocity preferences, depth preferences. As we acknowledge, we don't know enough about some of the turbulence parameters yet. But in this case here, this is from our workshop presentation that Mike and I contributed towards. You can actually set in motion these fish that are in the system. And so you can take that 2D output and sort of release them into your system and use the 2D output to see what is passable and start to think about, okay, each fish is thinking for itself based on its parameters and how many of those can make it upstream. Is there all of them or none of them? It begins to allow us using this 2D modeling to think about that passage success, because ultimately that's what we're designing a fishway for. We want to pass as many fish upstream as we can. And with this 2D modeling, you can begin to get at that and start to understand and utilize that for preferences in addition to the depth and velocity mapping that Mike and I talked about earlier. I don't know that we know enough to think true fish yet, but we're getting some initial thoughts in that direction. And so for that perspective, I think 2D modeling is very useful.
Sure. Why? So I've heard the same thing, Mike, that, the size of the fish, depending on the size of the fish, the 2D results can be more or less applicable to trying to anticipate kind of fish behavior. Why is that? Why can't a model with, let's say, 1 foot cells simulate the fish behavior of a 2-inch fish?
Well, yeah, exactly. I mean, it's a lot of the fish we're looking at are 2 to 3 inches, and so you're just not getting that resolution of what they're feeling. They're feeling an eddy, a turbulence that's in the 2-inch range. That's really severe to them. A big eddy that's in the 4-foot range, they're just going with it. That's really not a problem to them. So often, you got to look at what they're feeling, just like us humans. What it's got to be in our scale. Turbulence that's pushing us around is when we're swimming is kind of in our body length type size.
For sure. Yeah, I mean, I guess as you get smaller and smaller too, the depth average assumption that you have with a 2D solution becomes less and less valid, right? Because of the fact that that small fish is going to really experience that velocity and depth, or the velocity, not on an average basis. They're going to have that column velocity, and the location of where those higher and lower velocities is going to become a lot more impactful in terms of how that fish is moving through the.
And I think some of the video, there's some great underwater video of little fish where the velocity above is 6-7 feet per second, and they're just they're moving along the bottom between stones, just little bit at a time with no problems. So the 2D would never pick that up. So
yeah.
So in the same way, is it? I guess we have these sort of habitat suitability or passage suitability criteria, depth and velocities that are, stated for certain fish. And then we're using our 2D results to assess whether or not it's just a yes, no, is this passable or not? Is that kind of like a conservative assumption because of the fact that there are, in all likelihood, more passage routes in an actual 3D Nature Like Fishway than our 2D approximation of that?
Yes, it is, except that we don't know about the turbulence piece. So
yeah, sure.
You could be creating a barrier because it's too turbulent below. But yes, and I think a lot of the biologists from the agencies that review these, they're starting to understand that a lot of those criteria that came from basically flumes. It was the velocities that the fish felt versus what is really the models giving us, like you say, depth averaged, and there's going to be an area of lower velocity somewhere. In these
I think there's some of that relationship between the fish depth, the water depth, and the roughness depth, and how those all correlate. If they're all in the same order of magnitude of inches, the fish is going to have no problem navigating that. If your water's shallow, your fish can swim in shallow water, and your roughness is all over the place, they'll be great. So I think
Did you
just
have
keeping
something,
in
Chris?
mind that as we talked about the Hecraz cell size relative to fish length, I think also just sort of depth and roughness impacts as well.
Yeah, it's all interconnected.
So I want to know, how are these things performing? How do they work? Sounds really awesome, really cool. It's fun to model. I love doing that. But like, we've got enough of them out there right now, right? That we're getting results back. And how would this compare to, say, your traditional hardwired engineered fish ladder?
Yeah, it's a great question.
It depends.
Please tell me they're doing better.
Well, yeah.
I would say in the best of cases, they are equal to the best technical fishways, because there are technical fishways that pass very high percentage of the population that gets there. Oftentimes there's limitations around entrances. As with technical fishways, the entrance of a fishway dictates so much about a fish can even find it, let alone pass through it. I know what they're finding is, I think generally nature-like fishways have a lot more variability. So for a range of species, you're better off because you have more velocity variability across your whole fishway width. Like Mike showed in some of the parameters there for the physical modeling, you can see the deep zones in the center, your shallow habitat on the edges. You're going to have eels on the edges. You've got your stronger swimmers in the middle. And so for that range of species, they're definitely, I personally think they're better hands down for the suite of species across the board. I don't know if there's a published paper to support that, but unfortunately there are still some limitations and things we don't know with nature-like fishways, that there are some that are barriers and we're not seeing great attraction to even get the fish into them. And most often those are ones that are more of a bypass reach, or it's sort of a percent of the river flow. If all the river goes through it, inherently all of the water is drawing the fish to the fishway. Not to say you can't have a barrier, because you can still have bad hydraulics. I think, Mike, the general consensus is it's still, the studies that have been done included all nature-like fishways lumped together, bypasses, full channel widths, etc. And they don't necessarily outperform by leaps and bounds any of the other fishways.
But the big difference, and why I think there's a real push among the resource agencies that regulate fisheries, is they perform way better often for maintenance. They don't clog up with debris like a technical fishway. They don't require somebody to be out there regularly cleaning things out. They can adjust, the boulders move a bit, but they still function. Sometimes they even function better than when built. So that is what they like. If you're at a facility that isn't manned, every day or during high flows, but rather somewhere out in the woods or wherever that's fairly remote or not being maintained, like a road stream crossing, these are more reliable, I think, over the long haul.
And I would say, even from a very, very non-technical perspective, they just look more natural. They're more towards the natural side of things. You have to imagine that's going to be better for fish if we're getting closer to what nature has provided them over the millions of years we've been here, right?
That's the idea. Yes.
Good. Lastly, we only have a few minutes left, but I do want to give you guys both an opportunity to talk about what your favorite nature-like fishway or rough and channel project is that you've worked on over the years. You may have already discussed it or shown a little bit of graphics related to it during this conversation, but Tyler, I'll start with you. Is there one project that pops into mind in terms of one that was really rewarding and maybe challenging to work on?
Yeah, so I would say that was the one that we just built last year. I mean, I agree with Chris. The modeling is fun and iterating back and forth all over the place and coming up with these different parameters and looking at all of that is a lot of fun. But it's really fun when you get to put the yellow equipment in the water behind the cofferdam and start doing the work. You can really begin to get into what I think of as the fun aspect of that. Be able to take something that's not necessarily passable and convert it into something that is fully passable and has that habitat. This is the Shikellamy Nature-like Fishway project that we just constructed last year, about 120 feet wide, pre-project conditions in the upper left. This dam can be drawn down half the year. It's an inflatable bag dam, inflatable, bag, I guess would be essentially what you call it, or bladder. And so it only needs to pass fish for about half the year. But it's been in place, the dam has been in place for 60 years. The fish have had to stop at it essentially every year. But once we constructed that, we've got water now flowing into the entrance and coming down through. And we've got really good variability here from 3 foot of depth out through these boulder clusters into the floodplain where we've got very thin amounts of flow. And the fun part of this one for me was as we were pulling the stop logs at the upper end here, getting ready to release the water in, we had a little bit of water seeping through, and we had a little eel already swimming up through there. It was about a 12-inch eel, just swam right up to the stop logs and was sort of banging on them. I was like, all right, they're here, they went through, we just gotta open it up. So that was sort of the most recent one. It's probably always going to be whichever one I'm heading into construction or coming out of construction of, but that's one for me that I really enjoyed here on the Susquehanna.
Very cool. Mike, what about you?
Yeah, that's nice.
I mean, I would say the ones that are the most enjoyable are the ones that we've kind of gone and studied the most. I shared this one, which we learned a lot from, and the 2D modeling and seeing how it simulated the built project. That was really fun. Jameson Creek. Another was on a train crossing here, did similar post-project evaluation, learned a lot. These are the kind of projects I really enjoy learning from them, and therefore I kind of remember and get a lot out of them. And then I think the others, kind of what we're working on right now, which I showed some of the physical modeling. We're finalizing designs, trying to raise the monies for construction, which was the Turbulence Creek projects. We also, besides doing the physical modeling, we did, NHC did take the physical model results and did a CFD model, which here is their bed that they put into the open foam, open source CFD. And we learned a lot from that as well. So, I'm excited to build that one and do that post-project evaluation on this project. So, yeah. Very,
very, very cool. I do want to end the conversation today on something a little bit lighter, and that's something that I've touched on, or I guess as I've said a few times, and that is Rough Channel and Nature Like Fishway. For those that have been confused throughout this whole podcast, what's the difference between the two? Is there one that's right? What are your guys' thoughts on the debate between those two terminologies?
Well, the West Coast here, we often say Rough Channel, and Nature Like Fishway isn't a term that's widely used. So definitely came from Europe, I think, originally, and then went through the East Coast, has accepted that terminology. And I think maybe Nature Like Fishway is a broader context, like it could be log weirs, for example, could be nature like. Versus a Rough Channel usually is kind of like it's rock and coarse material through the entire project length, whether it be step pools with a rock pool bottom or such. That to me is kind of what a Rough Channel is.
Yeah, I'm being located on the East Coast. I've always called it Nature Like Fishway, and that's just what we think of it as. That's what some of the federal guidelines have come out as, is Nature Like Fishways. Not to say that that's always right, but through our discussions, Mike, I like the term Rough Channel better because it implies that it's an engineered structure. It's not just replicate nature exactly. There's a lot of thought and manipulation that goes into that creation of the channel. So I would say nature like has a connotation that for some people makes it think like it should provide all those ecological benefits of a natural stream restoration with your vegetation on the banks, and all of your macroinvertebrates can pass, and all that stream function stuff that we love may be present in a Rough Channel, but still at the basic level, it's a hydraulic structure to control flow, but it also has a goal of providing fish passage. And so I'm leaning towards embracing more the Rough Channel. I think, Mike, you guys are on the West Coast, have done a lot more work with culverts. And so I think working in a culvert, it's more of a Rough Channel. That's sort of just a generic, what a culvert bed can be thought of. You don't think about those, I don't believe, as a Nature Like Fishway inside a culvert. It's just a roughened slope. And that's what it is. So I'm coming around to that term. I think we use them interchangeably. I use them interchangeably, but I would say NLF is the highest level for anything that's trying to pass fish and represent something more natural than a concrete and steel structure. Roughened channel is maybe a little more accurate for what we're doing overall.
So it sounds like it's a little bit of a whiskey bourbon thing, right? Where all roughened channels are nature like Fishways, but not all nature like Fishways are roughened channels. So.
Maybe nature-ish instead of nature-like might be a better way. So, hey, I want to just quickly quiz our guests today before you close out, Ben, nice. Because I want to see how much they were paying attention to our questions, Raz questions. So, okay, guys, are we looking at diffusion wave or full momentum here?
Eddie there in expansion. He must be full momentum there.
There you go. All right, Mike. Way to go. Way to go. I'm glad you were listening, but you probably knew that already anyway. So
nice. Well, if nothing else on this podcast, we got an East Coast engineer and a West Coast engineer to compromise on language. So that's a positive outcome, regardless of whether anybody finds the content on this interesting, which I'm sure everybody will find very interesting. So. Well, this has been really, really great. Thanks, Mike and Tyler, again for making the time to have these conversations. Again, it seems to me like this is an area of water resources engineering that's continuing to grow and change and evolve, as so many things are within our industry. So it'll be really cool to see kind of where these topics and conversations are at in 5-10 years from now, particularly as technology continues to improve. We continue to get more data sets of calibration and verification of projects that are actually built. It feels like we're kind of at the forefront of some really, really exciting developments. So appreciate you guys taking some time to talk through those with us.
Yeah, it was a real pleasure talking with you guys today. Great to meet you, Mike. Keep finding these kind of opportunities, because that's just more opportunities for me and Ben to model them. So that's a lot of fun.
Yeah. No, thanks for having us. It's been fun to chat and hopefully provide some value.
Yeah. Thank you. Yeah.
Absolutely. And we will include a number of hyperlinks to references, studies, presentations that we kind of touched on today in the YouTube channel here. So if you're interested in following up with some of the resources or some of the presentations that Mike and Tyler saw and attended, we're going to include links to some of those in the chat.
And Mike and Tyler's personal phone numbers too, so you guys can call them up anytime you got questions. No, I'm kidding. Just kidding.
But yeah, make sure you add Mike and Tyler on LinkedIn if you want to follow them more. If you have questions, that's going to be a good place to reach out to them. And as always, if you have questions, follow-up questions on these topics or questions about HEC RAS overall, make sure to include those in the comments on our LinkedIn page or on the YouTube channel for this podcast. Again, appreciate everybody who was stuck around and listened to the conversation today. This has been Full Momentum and HEC RAS podcast. Until next time.